Now, welcome to the third part of this series of videos on dynamics of a system of particle. In this third part, we will be dealing with method of momentum for a system of particles. So first we will be dealing with linear momentum, which is very simple in case of system of particles. So as we have been doing all along, momentum, linear momentum for ith particle is given by this relation. Okay, mass of the ith particle into velocity of the ith particle. Now if you want to find total momentum of the system, let us denote it by capital L. That will be summation over I of Li, and this will be I Mi Vi. We can also write this using definition of velocity in terms of derivative of position. So linear momentum is given by summation over I of Mi dri over dt. This derivative can be taken outside, and inside you can write, because derivative is distributive, so you can take it outside, and inside you can write Mi Ri, and where from definition of center of mass, your RCM, position of center of mass, is 1 over m summation over I Mi Ri. So from this we can write summation over I Mi Ri as mass times position of the center of mass. So in the above equation, this will give me d over dt mass times t RCM over dt. Taking derivative inside will give me L is equal to, so I can take m outside and write drCm over dt, where drCm over dt is nothing but velocity of the center of mass. So our final relation for total momentum of a system of particles is total mass of the system multiplied by velocity of the center of mass. Okay, now if we take derivative of this relation, if I write L dot, then I'll get m VCM dot, so this will be m into acceleration of the center of mass. And in a previous video we have seen from Newton's second law for a system of particles that this is nothing but net force acting on the system. So we get total force acting on the system is equal to rate of change of total angular momentum of the system okay, where F is total external force on the system, and where L is total momentum of the system. Now from this you can also write expression for impulse. So if you like, for impulse for system can be written by integrating this. So dl over dt is equal to f dt from t1, sorry, we cannot integrate directly, so this is f. Now I'll rearrange, so this will be L dl is equal to f dt integrated from t1 to t2, this from L1 to L2. So change in linear momentum of the system is equal to impulse I due to total external force, net external force. So where I is impulse, linear impulse due to net external force. So you sum all the external forces and then integrate it to get this I. If net external force is 0, then your L dot will be 0 and L2 momentum of the system at a later time instant will be equal to momentum of the system at an initial time instant. When net external force is 0, so it might be that some particles are experiencing some force, but when taken in total, force applied by some external agency onto the whole system, onto all the particles, if you sum that up and that comes out to be 0, then you can write conservation of momentum of the system. So this is for conservation of momentum of the system. Conservation of momentum might not hold for individual particles if there are some forces acting on the particle, but it will hold for the whole system as long as net external force is 0.